Hey guys, welcome back. In this video, we are going to look at one application of Menger's theorem. Suppose we have the following graph G with the vertex U and V as identified. First, we want to find the kappa prime of UV of this graph. Namely, we want to show that this number is equal to 5. Well, we're going to make use of the edge version of Menger's theorem, which says that kappa prime of UV is equal to lambda prime of UV. So instead of finding kappa prime of UV directly, we're going to find lambda prime of UV. Let me remind you what are kappa prime and lambda prime. Kappa prime of UV is the minimum size of a UV edge card in the graph G, whereas lambda prime of UV is the maximum number of pairwise edge disjoint UV paths. Alright, let us now look at the graph G. So the idea is to find lambda prime of UV, which will give us the value for kappa prime of UV. Well, first of all, notice that any UV path will use one of the edges incident with the vertex U. So if we are considering edge disjoint paths, then there can be at most 5 such paths, because there are only 5 edges which are incident with the vertex U. So this observation gives us an upper bound on the number lambda prime. Okay, so let me write down here lambda prime. It's bounded above by 5. The reason being, any edge disjoint UV path must use one of the edges incident with U. Okay. Next, we're going to find a lower bound for lambda prime. Remember, lambda prime is the maximum number of pairwise edge disjoint paths. So the keyword here is maximum. In other words, if we can find a set of pairwise edge disjoint paths, then this number must be at least the number of edge disjoint paths that we found. Okay? So here I'm going to give a set of 5 pairwise edge disjoint UV paths. Let me call this path P1, which is given by the path using the edge UA followed by AE, EI, and IV. We're going to denote this path P1 by UAEIV. So this is an UV path. Next, we have path P2 given by the edges UB followed by BE, EJ, and JV. So this is another UV path which is edge disjoint from the first one. Next, we have another path. Let's call it P3. This time we have the edges UF, FG, and GV. So this path UFGV is a UV path which is edge disjoint from the previous two paths. Next, we have path P4, and this is given by the edges UC, CH, HK, and KV. And let us denote this path P4 by UCHKV. Again, this is edge disjoint from the previous three paths. And finally, there's another path, P5, which uses the edge UD, DH, HL, and LV. So we denote this by UDHLV. And this is again edge disjoint from the previous four paths that we have found. So altogether, we have actually found 5 paths which are pairwise edge disjoint. Therefore, lambda prime, being the maximum number of such paths, must be at least 5. Do you follow me? Lambda prime of UV is at least 5. And hence, together, we conclude that lambda prime is exactly 5. And by Menger's theorem, this must be equal to kappa prime of UV. Okay? So we note here that the second equation follows from the edge version of Menger's theorem. So this settles the first part of the question. Let us now look at the second part of the question. Now, in the second part of the question, we want to find a set F of 5 edges such that U and V lie in different components after deleting F from the graph G. In particular, if F consists of UA, UB, UF, UC, and UD, then upon deleting these edges, U and V will lie in different components of G minus F. So that is pretty straightforward. Let me just write it down here. If we let F to be the set consisting of UA, UB, UF, UC, and UD. Clearly, this is a set of 5 edges. Then F is an UV edge card. So U and V will lie in different components of G minus F. And we are done. Okay? Right, let us now move on to the second part of the questions. I mean part 2 of the questions. Here, we want to find lambda of UV of the graph G. Namely, we want to show that lambda of UV is equal 3. Again, in the spirit of Menger's theorem, we are not going to find this directly. Instead, we're going to find this indirectly by using the vertex version of Menger's theorem. Remember, the vertex version of Menger's theorem states that lambda UV is equal to kappa UV. Let me remind you what they are. Lambda UV is the maximum number of pairwise internally disjoint UV paths. On the other hand, kappa UV is the minimum size of a UV card. Alright, let us now find the number kappa of UV for the graph G. First of all, let us determine a lower bound on the number kappa of UV. To do this, we shall find an UV cut. Well, it's not hard to see that the set U containing the vertex E, F, and H is an UV cut. Since deleting the three vertices E, F, and H, the graph will get disconnected and the vertex U and V will fall into different components. But remember, kappa is the minimum size of an UV cut. And since U, the set U, is an UV cut, this implies that kappa of UV must be at most the size of U, which is 3. Alright? So we have obtained an upper bound on the number kappa of UV. Next, we will show that kappa of UV is at least 3. Well, this is equivalent to saying that deleting any two vertices from the graph G will not make the graph disconnected in such a way that UV falls into different components. Let me write down here. If we want to show that kappa of UV is at least 3, then this is equivalent to showing that the deletion of any two vertices will not make U and V lie in different components. Alright? Well, to verify this, I'm going to make use of the fact that there are 3 pairwise internally disjoint UV paths. Here are the 3 paths that I'm going to use. The first one is called P1, which is the path given by UAEIV. The second path, denoted by P2, is the path UFGV, and the last path, P3, is the path UDHLV. Well, we can visualize these paths in the picture as follows. P1 is given by the red edges, and P2 is given by the green edges, and the last one, P3, is given by the purple edges. So we have P1, P2, P3, which are pairwise, internally disjoint. Now, what is so important about having 3 such paths? This implies that deleting any 2 vertices from the graph G will not separate U from V. To see this, let us visualize U and V being connected with 3 internally disjoint paths. So what's the worst case scenario when deleting 2 vertices from the graph G? Well, the worst case scenario happens when these 2 vertices lie on exactly 2 of these paths joining U and V. For example, the first vertex we delete could lie on the first path, and the second one on the second path, or the first one could lie on the first path and the second vertex that we delete lie on the third path. Or it could be the case that these vertices come from the second and the last path over here. In all cases, notice that deleting these 2 vertices will never separate U from V, because there is always a path connecting U to V. And hence, U and V will never lie in different components upon deleting 2 vertices. Do you follow me? So we have proved that the deletion of any two vertices will not make U and V lie in different components. That is, the number kappa of UV is at least 3. Together with the lower bound, together with the upper bound that we have proved earlier on, this implies that kappa of UV is exactly 3. And of course, by Menger's theorem, this number must be equal to lambda of UV, which is required by the question. Alright, so this settles the first part of part 2 of the questions. Let us go back to the second part of part 2 of the question. Here we want to find a set U of 3 vertices such that U and V lie in different components of G minus U. Actually, we have found this set earlier on. Namely, this is given by the set U containing the vertex E, F, and H. Clearly, this is a set U of 3 vertices, and the deletion of these 3 vertices will make U and V lie in different components of G minus U. Okay guys, we have come to the end of the questions, and I hope that the solution makes sense. Okay guys, see you next time. Thank you.